Hello, we are on to our next kinetics discussion. This time, we're going to look at rate laws, specifically how to determine a rate law through the method of initial rates. So, two different rate laws. The first one is the differential rate law, which we're going to work on today, showing the relationship between the concentration of reactants and the rate of the overall reaction. The differential rate law is usually just called the rate law. We don't use the word differential. The next time we meet, we will talk about the integrated rate law, which expresses the relationship between concentration of reactants, just like the differential rate law. However, this time it's related with time. So kind of a big distinction there. So rate law of a reaction is the mathematical relationship between the rate of a reaction and the concentration of the reactants and a homogeneous catalyst as well, if they are using one. Not have to use one, but you can. Now, the cool thing about rate laws is you can only figure them out experimentally. There is nothing to look up in a book. There is no articles to read. I mean, you could read about what other people did, but everything must be done in a lab to determine what's going on with that relationship, with that reaction. So it kind of forces you to do experimentation in order to determine it. You can't just look it up. You can't Google it. Sorry. The rate of the reaction is directly proportional to the concentration of each reactant raised to a power. So it's pretty simplistic in that sense. So given a reaction of A going to A plus B go to products, a rate law has a general formula that we'll look at. Usually they use N and M are called the orders. Those are your exponents, or the powers, if you will. The lowercase k, and I explicitly are saying lowercase k, is the rate constant. Capital K is not the rate constant. It is the equilibrium constant, which we'll see in our next topic. So realize, same letter, lowercase versus capital. So here's our our rate law. Rate equals K times the concentration of A raised to some power N. Honestly, it doesn't matter what exponent letter you use, X, Y, Z, A, B, C, G, H, I, doesn't matter, as long as it's not the same as something else. And if you have more than one reactant. But all rate laws have this general formula of rate equals the rate constant times the concentration raised to some power. Now, these orders, the exponent or the power is called the order. The exponent on each reactant in a rate law is called the order with respect to that reactant. So it's specific to how that reactant is affecting the rate. If you add up all the exponents, they give you what is called the overall order of the reaction. So individual reactants have their own individual order, but the overall reaction order, just add them up. Pretty simple math. The rate law for a single step reaction. Now, the catch-22 here is you have to be explicitly or specifically told that the reaction is occurring in a single step. If you are not given those instructions, you cannot, I repeat, you cannot assume it's a single step reaction. However, when you are told it is a single step reaction, the coefficients in the reaction are your exponents. No math to do, nothing to solve. You literally just take the coefficient of reactant A and you make that the exponent in your rate law, and the coefficient of reactant B, and you make that the exponent in your rate law with respect to B. So it makes life easy in that sense. feel like I'm missing something there. This is a colon, but I'm not too sure what's going on. So we'll maybe come back to that. All right, reaction order. So let's just say this is a single step reaction for argument's sake. 2 nitrogen monoxide plus oxygen gives us 2 nitrogen dioxide. The general rate law, or the rate law, will be rate equals K, the rate constant, times NO to the second power, because it matches the coefficient in the reaction, and oxygen to the first power. We do not include 1 or first, because there's a 1 with regard to oxygen. So we know it's second order with NO, and we know it is first order with oxygen. Add them up. The overall order is going to be 3 or third order. Again, this only works when you are told it is a single step reaction. And this now makes sense that my colon on the previous slide corresponds to this. I just had a brain fart. Yay. All right, so writing a differential rate law. Let's go through the steps on determining this. So here's our reaction. We want to write the rate law, determine the numerical value and units of the rate constant, and the overall order. So when you're doing method of initial rates, that you can see, where's my mouse? There it is. We have to use data. The type of data we have here is you're running multiple experiments, and you can see that the concentrations of my 2 reactants are changing, and the rate changes accordingly. So the goal here, when trying to figure this out, is pick one of the reactants to solve for first, after you kind of write your general equation. So part 1, we want to determine our exponents. So here's our reaction. Let's go back here. Notice there's a 2 with NO and a 1 with chlorine in the balanced reaction, but this is not single step. So in my general rate law, I'm going to just have X and Y, or any letters you really want for your exponents. Now, in order to determine your exponent, the goal is pick 2 experiments where the concentration of what you're looking at changes by some factor, but the other one does not change. So let's solve for nitrogen monoxide first. Which 2 experiments have nitrogen monoxide concentration changing, but the concentration of chlorine remains constant? So experiments 1 and 2, we see chlorine is constant while NO doubles. So I look at this and I'm like, oh, okay, so NO is doubling. What's happening to the rate at the exact same time? The easiest thing to do, if you can't see it in the data, is take the second experiment rate and divide it by the first experiment rate. So if we do that, we see that the rate quadruples. So the reaction is second order with respect to NO. Now, mathematically, to show this, I would write down 2 raised to the x power, where the 2 represents a doubling of nitrogen monoxide. X is your exponent you're solving for. So 2 raised to the x power equals, now rate is quadrupling, so 4. 2 to the x equals 4. If you solve for x, you get 2. That's why NO is a exponent of 2 or second order. So now rate equals K times NO to the second power times chlorine to some unknown. Questions? All right, well, let's solve for chlorine. Again, same idea. Pick 2 experiments where the concentration of chlorine is changing by some factor, and NO is remaining constant. We'll pick experiments 2 and 4. Yes, you could have also picked experiments 1 and 3. Theoretically, it shouldn't matter, but let's just go with this one. We see that NO is constant at 0.5, and we see chlorine is also doubling. Now again, ask yourself the question, what's happening to the rate? So I'll set up my equation, 2 to the y, 2 representing chlorine's concentration being doubled, y is the exponent you're solving for, equals what factor is rate changing? Well, according to the rate column, the rate is doubling. So 2 to the y equals 2. If 2 to the y equals 2, what does y equal? Y equals 1, so I know that it is first order with respect to chlorine. So now I have my rate law. Yes, this happens to match the coefficients in your balance equation, but it's not always going to happen that way. Never assume it will. If you are given data like this, you have to do it experimentally and show your work. Again, the work to raise some factor raised to some power equals the factor that is the change in rate. Solve for your exponent, and that's all the work you really need to show. Now, determining the value for K in the reaction, in your rate law, is pretty simple. If you're given, again, I gave you 4 experiments. Theoretically, you can choose any of the 4 experiments, plug the data in, and solve for K. For this example, I'm just going to choose experiment 1. Now, one thing to note here, the rate constant can have different units. It's not always going to be the same set of units. So you have to solve for both the numerical rate constant as well as the units. College Board in the AP exam will ask, determine the value of the rate constant and its units. If you don't put the units down, you don't get credit. You don't lose credit, but you don't get any credit. So we plug experiment 1 in to our rate law. You guys can do the math here with a calculator, but please notice what's going on with the units. Remember, if you square something, it squares the number and it squares the units. Plug everything in, and we get liters squared per mole squared times second. You could also represent liters squared per mole squared as 1 over capital M. Remember, capital M is molarity from solutions. So you can kind of simplify your answer as 1 over capital M squared, or capital M raised to the minus 2. Many ways to represent it. But again, realize, look what happened to the units, as in, there we go. These become mole squared, liter squared, times mole over liter. There's your liter cubed per mole cubed. When you bring it over to the other side, because you're dividing, it flips. So units play a very large role in kinetics. Got to be aware of that. Any questions? Overall order, it's a 2, it's a 1, add them up. Pretty simple. Yay. All right, so we have rate equals rate constant times a to some power. Couple things. If a reaction is 0 order, the rate of the reaction is always the same. So anything raised to the 0 order when you're solving for your exponents, you will not include it as part of your rate law. Not even raised to the 0 power, just erase it, don't include it. When we double A, will have no effect on the rate because it's 0 order. Remember, if it's 0 order, what's anything raised to the 0 power? It's got to be 1. So it kind of makes life easy in that sense. If we know it's first order, we know it's directly proportional to the reactant concentration. So if I double A, it has to double the rate. Because what's 2 raised to the first power? It is just 2. Makes life easy in that sense. If the reaction is second order, so let's say N is a 2, it's directly proportional to the square of the reactant concentration. So if I double A, it will quadruple the rate of reaction. Now be prepared, you're going to come across fractions in your orders, like maybe to the 1/2 or to the -1/2. Or you're going to be, instead of doubling the concentration, you're going to half the concentration. Or you're going to 1/3 the concentration. Fractions will play a role, so please be ready for that. Thank you very much.